Hey everyone! So in a recent video, we took the limit as xy approached 0, 0 of a function, right, of two variables. And we found that we approached one value along one path and then approached something else along a different path. And that showed that the limit didn't exist. But how, if the limit does exist, how can we show the limit is the same along every possible path if there's an infinite amount of paths? Well, one technique that I particularly don't like that much is using the squeeze theorem, which I'm not going to get into here because I really think that using the technique of converting to polar coordinates is, in my view, much easier. I like polar, and I think that you guys should really learn to love polar too. So how do you convert the polar coordinates? Well, we know, right, in polar, we know that x is just the same as r cosine theta. And y is r sine theta, right? Okay, so how is that going to help you? Well, let's convert to polar and watch how cool this can be. Okay, we're going to convert everything to polar. So x, right, x is r cosine theta. That's always true. Y is r sine theta. So let's just instead of the limit as xy approaches 0, 0, we're taking the limit as r approaches 0. Of what though? Of, well, x is r, so we have r cosine theta, okay, times y. So this is x, and then it's times y. Well, y is r sine theta, okay, r sine theta, okay, over, well, the square root of x squared plus y squared. Now, there's actually, well, I can show you a true. Let's actually go about this this way. We could, if you know that x squared plus y squared is r squared, that might simplify things even more. But let's say you only know that x is r cosine theta and y is r sine theta. Okay, well then x squared is what? That's r cosine theta squared, right? That's r cosine theta all squared plus y. Well, y is r sine theta, so we have r sine theta. But then that is all squared, and then it's the square root of all that. Okay. Well, can we clean this up? Absolutely. What do we have on top? We have, well, r times r. Let's say we have it, so we have the limit as r approaches 0 of what? R times r. We have r squared times sine theta times cosine theta. So we have r squared sine theta cosine theta, okay, over, on the bottom, we could factor, we're going to be an r squared here and an r squared here. So we can factor that out and do the square root of r squared times, well, sine theta, right? Sine squared theta plus cosine squared theta, right? If you were to multiply this, you get a cosine r squared cosine squared plus r squared sine squared. You can factor out the r squared and get r squared times sine squared plus cosine squared. Okay, and we're still under that square root. Well, what is sine squared theta plus cosine squared theta? For any theta, that's always 1. This is the identity you should definitely know. Sine squared plus cosine squared is 1. So this is r squared times 1. Oh, but that's just the square root of r squared, right? So that's r. So this equals the limit as r approaches 0 of, on the bottom, we're just going to have, right, r squared times 1. So that's r squared. But it's the square root of r squared. So that's just r. So that's just r, but we have r, so we have r squared over r here, right? Well, that just becomes r, right? R squared over r is just r on top. Okay, so this limit equals the limit as r approaches 0 of what? We just have an r on top. We just have r times sine theta times cosine theta. Okay, and we're taking the limit as r approaches 0. What do we have? We have 0 times something. That's 0. This limit equals 0. That's it. We never have to convert back to x's and y's, right? We convert to theta, and we got the limit to be 0. Always. Right? The limit is always 0. No use, no need for the squeeze theorem. Just convert the polar, and the limit is 0. So thus, the limit as, right, of our original function, as xy approaches 0, 0, of xy over the square root of x squared plus y squared, that is always, no matter what path you take, it is always 0. So thus, the limit is 0. Cool. All right. Be sure to like this video, subscribe, and I'll see you all really soon.